Okay, we have exam 2 here for modern optics. The first section is a multiple choice section, GRE style. First question is, if the wavelength doubles, what happens to the wave number? Well, the wave number is 2 pi over lambda. So that means the wave number goes inversely when you want to relate it to the wavelength. So if you double the wavelength, then the K will be 1/2, it'll halve. So the correct answer is B. This next one here, you have 3 different lenses, and you have 50, 100, and 400, 2000 were used. Now, 3 of them are going to be used in there. It wants to know what C was taken with. Now here, remember the relationship that your relative magnification for telephotos, it's a nice formula where you look at the focal length that you're dealing with and divide by 50 millimeters. So if you have the 50, then it's 1. If you go with the 100, then it's like 2 times. This is a formula that's good for telephoto lenses when you have the long focal lengths. So if you look at these two, this distance here, if we go from here to there, that distance over on this one looks like the Biltmore house here, this is like double this. Because see, these are all related with simple ratios. So in other words, if you have a 50, this is double, this is 4 times, and this is like, man, like big time. So if you're looking at C, I think here the key is to look at C and A, compare those two, that A has to be twice the focal length of C. And the only ones that have that 2-to-1 ratio are these, which means this would have to be the 50, and this would be the 100. And I have no time to even think about B. I'm taking an exam. Time is precious. I answer the question, and I go on. So C is 50, and choice B, and we go on. So now we go here to the third question in the multiple choice. And this one has to do with 4 pictures, and we have a 50, a 28, and a 70. We have a similar idea. Now, it says B was taken with 50. All right, so this is the 51 right here. This is the 50 millimeter. And we can do a similar sort of thing to estimate things. Well, first of all, I notice that this is a wide angle compared to this. So the A is a wide angle compared to this. This is a little bit of a telephoto shot, since this form here looks closer, a little bit bigger. And this is way telephoto, so I know that immediately this is 28. This is the wide angle. This has to be 28. Now, I know they didn't ask for A, but if it's that easy, I go ahead and put it down. So then the fourth photo, this one here, this is telephoto shot. This one could be the 70, or could be beyond that. So it could be here. I don't see 70 as a choice. So I'm looking at these 2 choices for the telephoto, because these are wide angle. So these all get crossed out. So this telephoto. So then the question is, if it's a 210 or a 700, that means that by logic, this has to be the 70. C has to be the 70, because D, there's no 70 here. So by logic, 70 is here, and I gotta compare this to 70. So if this is 210, this has to be triple the magnification. If it's 700, it has to be 10 times. Well, see, all of this looks like it's around in there. So it's no way 10 times. It's more like It's more like 3 of these things. So we want to go here with the 210 one. What's the focal length of 20 centimeters if you place them together? Well, diopters add, so remember your formula. You add diopters, and the 20 centimeter would be, remember your diopters, is going to be, you take 100 and divide by F in centimeters. So if you have 20 centimeters, you're talking here 5 diopters. And if you put them both together, you get 10 diopters. But remember, you can go back to get the centimeters if you take the 100 over diopters. So step 1, 5 diopters, diopters add, 5 plus 5 is 10. Then put the 10 in for the D here. This is the combo. I'll put down C for combo. Then that's going to be 10, and 100 divided by 10 is going to be 10 centimeters. If you have 20 centimeters and 20 centimeters, you're going to be bringing the focal length in even closer, because the strength is, you're hugging. And if you have 2 of these, you're going to hug some more. So that means you could eliminate these immediately. And that kind of helps. And 0 would be super strong. And we go on to the visual acuity of the eye. Well, you're supposed to read the 20-30 line at 30 feet. So if you could do it at 40 feet, like you're doing better there. So that, if you're doing better, that means there's no way it's going to be that one. Okay, so here, what we might do is say, well, I forget the formula. Well, then we take 30 and 40, 3/4 or 4/3, and if you multiply by 20, say on 3/4, you're going to get 15. And if you multiply on 20, 4/3, you're going to get something that's 7, around 28 or so. Now here, 20/28 is bad vision. I mean, it's not as good as 20/20, so it can't be that one. So it's got to be the 15 one. It's got to be this one there. Now, the myopic eye, if you can see anything closer than 200, remember with the myopic eye, you want to bring in to 200 the mountains. So that means you want your focal length to be minus 200 centimeters, since you're talking here diverging lens. And when you do your diopters, remember you take 100 over F in centimeters, which would be 100 over a minus, the minus sign goes to that 200. So that's minus 1/2 diopter, and that would be then this one here, minus 1/2 diopter. Okay, hyperoptic eye. So for hyperoptic eye, remember, for a hyperoptic eye, you need to be able to read something that's at 25 centimeters. So the rest of the eye, the regular eye does 60 diopters, and this is an easy way to analyze it. You need an extra 4 diopters to be able to bring something from infinity, to a book 25 centimeters, 10 inches away to read it. So you need 4 diopters. Now, the best you can do here, again, 200 centimeters, but in this case, the person can't read anything closer. So that means the best that they could do, well, we already did the 200 case, that's going to be 1/2 a diopter. But they need to do 4 diopters, so you have to prescribe the difference. So you want to prescribe the 3.5 to get them to be able to see at the right distance for reading. So for MC8, think of these glasses as being neutral, like a regular pane glass window. Then the letters would be like the L, these would be the same size. In other words, the same size. You would basically see like this chart would be, the letters would be the same size of the chart. So here, if you go away from that chart, like this is going away more from the chart size than this one. So that means this one has to be stronger. And like we just like finished right there and don't need to think about it anymore. So the right ones have to be stronger because the size here deviates more from what it would be. Like here, this would be your regular size there. And just compare these two is probably the best way. Since this is smaller than this one has deviated more from the chart. And now we come to the one with my mother, all right, holding me. And here, I needed diverging lens because I was nearsighted, couldn't see the blackboard in high school. And so that means the way you want to think about this now, here we didn't cover refractive error, but all the things you need are in the problem because it's basically telling you the refractive error is the negative of the eyeglass prescription, which kind of makes sense that by putting the glasses on, I have no refractive error, like I'm then considered normal. So my mother needed glasses plus 1.5D, so her refractive error was going to be here opposite that, so it's the negative. So then if you take my glasses off and give them to my mother has a refractive error of, here it's given, it's the opposite of this, minus 1.5D. If you give her my glasses are going to push her an additional -5. So my glasses will push her to then -2. A -2 diopter error, and when she put those glasses on, she flipped out and said that I really had bad vision, and in reality, she had worse vision. This one here, to correct for spherical aberration, remember spherical aberration is that the margins bend too much. That's how you remember the spherical aberration. The marginal rays bend too much. So you want to be less curved at the end for the cornea. That'll counteract that. And the crystalline lens have less index of refraction. So you have your cornea and you have your crystalline lens. So if the edges, if this is flatter and this has a less index of refraction, that'll take care of solving, the problem. That's it. So let's look at here the first problem. And the first problem here we have the telephoto converter. And you remember the telephoto converter goes between your regular lens and the camera body. So this is the setup. This is a telephoto lens, but you're going to be using a teleconverter to promote your lens to a telephoto. So that's the setup. And this is giving you the focal length, the back focal length here, which is given as the 50 back in here. And this is your formula, where you have your distance here, D, between the two lenses. This is your formula that relates everything. So, and these were given to you on the exam here. You don't have to memorize these. So what we're asked to do is we're asked to solve for the focal length of the second lens, the f2, and the D, because we know the f1 is going to be the 50, and the only two things that are missing here would be the f2 and the D. So you're basically looking at two equations that have two unknowns. That's what you're looking at. So what's the best way to solve it? Well, I notice that the denominator is the same in both cases. So I think what I'll do is divide one by the other to get rid of that denominator. Okay, so if we do that, say we take the F and divide by FB, then that would give me an F1 and an F2 upstairs. And when I divide by the FB, this numerator now goes in the denominator like that. And then they get the cancellation of this mess here. So that's very nice because that cancels even, and that gets you a nice equation like this. And now if you want to plug in some values, we know that F1 is a 50, so 50 goes in there. And we know that the back focal length is also 50. This is also 50. And there's one thing in the problem that we didn't look at yet, and that is this teleconverter is given as a 1.4 teleconverter, which you can even see written on the teleconverter. So that means it takes 1.4 times your 50, which is your regular lens that you use. That's how that works. So we're going to plug in all this stuff. We then get 1.5 times 50 divided by 50. That's the left-hand side. And then the right-hand side is 50 over 50 minus D. Now, what's neat about this is that's gone. And that means 50 is equal to, so what I'm going to do here is take the 50 over 50 minus D, which is equal to the 1.4, and I'm just going to swap these and go 50 over 1.4 is going to be 50 minus D, just like swap those two. You know, multiply both sides by that denominator and divide, or just simply 6 divided by 2 is 3, 6 divided by 3 is 2. We always swap there. So when we do that, then we're going to get here for this, D is equal to 50 minus the 50 over the 1.4. We plug in the numbers in the calculator. This will be 35.71, and this will be 14.286. And at this point, I don't want to round anything off yet because I'm in the middle of doing the problem. So, you know, we're going to leave that as the millimeters for now. And then we're going to go to figure out now what the D is. So with the algebra, there's different approaches. I'm going to use this one here, that F is F1, F2 over F1 plus F2 minus D. They both have the same denominator, but that looks a little friendlier to me than all that stuff. So I'm going to use this one. And then what we're going to do is for the problem here, what you can do is you can replace this with the 1.4 times F1, because that's our teleconverter formula. See, then these things go. And then we have the formula 1.4 is F2 over F1 plus F2 minus D. And this is going to be then 1.4 is F2 over 50 plus F2 minus the 14.286. So we get 1.4 times 50 plus 1.4 times F2 minus 1.4 times 14.286 is F2. That's like taking all this and bringing it to the left-hand side. And then we find, when we do that, if we look at these two, you know, subtract, this will be 0.4 times F2, and then I'll take everything else on the other side of the equation, 1.4, the 14.286, and then this, that goes over as a plus, this goes as a minus, and there's a 1.4 times 50, so I have this. And then when I work this out, I got a minus 50.00, and then when I divide, I get minus 125.5 millimeter. But now you have to be careful. I would report this as 14.3 if it were up to me, and I would report this as -125 if it were up to me. But my client here, who's paying me, wants this. So that means I need to do 14 millimeters. And then I need to do here -130 millimeters. Or you can go centimeters if you want. Then this would be -13 centimeters. And this would be 1.4 centimeters. All right, that's important. That's what the client wants. That's what the client gets. Okay, now we move on to the dioptic power one. And for this one here, what we do is we have a formula given to us, which is nice, and we have all the N's, and we have the R's. So the only thing tricky about this is what do you put in for R1 and R2 in terms of, like, you know, is it going to be positive or negative? Because that can be a little bit of a problem. So what I did first off is I look at, say, an enlarged version of this, and if I'm going here, and this is a normal, and this is 1.2 N, and this is 1.4. So if I'm going to a more optically dense material like air to glass, I know I bend toward the normal. So that means this is diverging, this is negative power. So this one here, this first one here, has to have negative power. So if N2 minus N1 is positive, R1 has to be negative. And you may say, well, maybe you remember that from class, that cut, you know, is going negative, but I like to always check it this way. Then if I go to, say, this next surface here, like if light were coming in like here, say, like that right there, then I got to know what this N is. This N is 1.6. So here I'm going like I'm going into more dense. So that means I've been toward the normal again. So that's a negative power. So this is also negative power. So if I have N3 is positive, more positive than N2, this is positive. And then if I put in R2 as a negative curvature, so you can think of it negative curvature, then you're going to get the right answer. So now it's just a matter of putting in the numbers, all right? So the put in the numbers, and it said you could get partial credit if you did them separately. So this is the total power, this is power 1, N2 minus N1 over R1. So that's going to be equal to 1.4. N2 is the one in the middle, 1.4, minus the first one, 1.2. And then I'm going to divide by the negative to make sure I get the negative power. And R1, 4 millimeters. I like to do it like this and put in my meters. So then I can get my diopters directly. So see, 1, 2, 3. If I move over to the left 3 times, then millimeters, 4 millimeters becomes this for meters. And then this comes out to be minus 50. And I'm going to keep a couple extra figures here, minus 50 diopters. And if I go to the next one, because I'm going for partial credit here, this is N3 minus N2 over R2, and N3 is the 1.6, the N2 1.4, which we already used. And see, that's a positive quantity. I know this is going to be a negative power, so I need to have the negative sign for the R2. And since that's 6, I'm going to go 0.006. And when you work that out, you get minus 33.33 diopters. Then the last step is to use the formula minus D over N2, but I recognize these are the powers that I already have calculated. So I'm going to call this here power 1. See, that's this one up here. This one is here. And then power 2, it kind of makes the math easier for me. So the D is the 1 millimeter, so that's going to be, that minus sign is from there. The D is going to be 0.001. The N2 is the one in the middle, the 1.4. And then here I have my powers, my minus 50 from up here, and my minus 33.33 from there. And then when I calculate all that stuff out with the calculator, this gets me minus 1.190. Then it's a matter of just adding them all up. And if you add all these up, this is gonna be like minus 83 or something. And then here's another minus, like minus 1. It's like a minus 84. When you do it on a calculator, it turns out to come out to 84.5 D. And then here, the problem here wants 2 significant figures. That's what the client wants, so that's what the client gets. This is minus 85 D. That takes care of the next problem. Then the last problem here is a group velocity problem. It wants me to find the group velocity, and here it actually tells me what the group velocity formula is. That was nice. So I need to find omega as a function of k. So I go looking for, where is omega? Where is omega? Here's an omega. So in other words, the omega is the energy over h bar. And I don't really care what all these things stand for. It's to do the problem. I'm just going to logically, follow the yellow brick road, so to speak. You may know these from another physics course, and you do it in modern physics, but you really don't care. I don't care. I just want this. And now I don't see here any k's. So I go to my E and say, oh, here's my E. And my E is going to be then 1/2 mv squared over h bar. I still don't see any k's. But I see that the k is coming from here, and I see there. So I'm saying k is 2 pi over lambda, but from this one, 1 over lambda, if I flip this, is p over h. So that means this is 2 pi p over h. And then it's telling me here's h bar. So h over, oh well, let me just go ahead and fix and get this over here. This is h over 2 pi k. So this is then h bar k. All right, now we have progress, because see here, there's an old trick that if you take the momentum and square it and divide by the m, that gets you v squared. So in other words, an old trick here that's used a lot in physics is just to multiply top and bottom by m, like this. And then this is 1/2 p squared over m. So then when I get this far, I can now replace the p with the h bar k. So this is h bar squared k squared over m, 1 over h bar. This is going to be 1/2 h bar k squared over m, and now I can take my derivative because I have omega in terms of k. So d omega dk is 1/2 h bar over omega 2k, which is h bar k over m, and the h bar k is the momentum. So this gives us here d omega dk is the momentum over p, but the momentum is mv. So the most elegant answer here is the velocity. How about that? The group velocity for this particle is the velocity of the particle. Nice, very beautiful result. Okay, that does it. the exam solution.